I just want to start off with errata. So firstly, I said that on the stable module category, sigma squared is the identity, and that's just false. Okay, so it's true. So somehow I spent like a large amount of a couple of years ago thinking about Z mod PZ, where this is true. So that is false. And also there's I made a mistake in the Brouwer tree of the principal block of B, which I'll fix. So mistake in. Okay, so fixed for that. It's a very innocuous looking mistake, but I just don't want someone to be sitting at home going, what? Geordie said this is P plus 2 and it's P plus 1. Fix today. Okay. Yeah, I think Alex pointed out this error. Firstly, the other thing that I wanted to, this is in some sense an extended erratum, thanks to Akia's questions last time. I just want to get the Brouwer tree story straight, not because it's particularly, it's not super important, I don't think, unless you're like really hardcore, want to understand blocks with cyclic defect group, then definitely you should know what Brouwer trees are. It's not that important, but I still think it's very nice, and so I'm just going to explain that for a page or so. So Brouwer trees. So remember that to a block, be a block with cyclic defect group. So we have this, B is a block of the representations of a finite group. We can associate to this block a defect group, which measures how complicated the block is. The more complicated the group, the more complicated the block, basically. So with defect group D. And now, if D is cyclic, which is a pretty simple group, not in the technical sense of simple, but it's a pretty easy group, it's a cyclic group. We can associate a planar tree plus optional, I think I didn't emphasize that last time, but optional exceptional vertex.
Then the exceptional vertex is not part of the data, like it's deducible from the rest. Or...
So what I'm saying, I'll draw a picture. So I'll draw two pictures. So this would be an example. So here's my planar tree. And then I have one vertex. So I can have at most one exceptional vertex. And I label the exceptional vertex with a number which is bigger than or equal to 2. The multiplicity. Another example would be this one. Now, and I'll just say in words what I said last week, or whenever I said it. You have this planar tree. This tree determines the block up to Morita equivalence. So it determines the category of representations. When you look at derived categories, the only invariants are the number of vertices and the degree of the exceptional vertex. So it's a really beautiful, simple example of the fact that passing to derived categories allows many, many things to become derived equivalent. Okay. Now, I want to explain to you how to get the Morita equivalence class. So we associate to this a quiver, and what I'm going to do is I'm going to draw the quiver in a different color. So the quiver, I'm just going to draw on top of this graph. So we take one vertex for every edge. And then we draw clockwise arrows. And the reason that I included this example, is because if you have an exceptional vertex, which is on the end like this, we also include a loop around the exceptional vertex. So this was Alex's question. Why can't it seemed like these things could never have loops, and they almost never have loops except when this exceptional vertex occurs on the end. So this is exceptional vertex What do you call the number of edges incident to a vertex in a graph?
To degree.
Great. What is exceptional vertex of degree 1 implies we get an extra loop.
Sorry, Geordie, are we using the degree of the exceptional vertex also as the number n? Like, are we overloading the word degree?
No.
Oh, it's multiplicity. Okay.
And I just want to, so it's a little bit confusing. And I find if you read notes on this subject, it's extremely confusing because you have the graph and then you have the quiver, and somehow vertices of the quiver are edges of the graph. But anyway, so I'm just gonna put a few different, so here's A, B, and C. So any vertex B of graph, not of the quiver, gives rise to the notion of a V cycle. So, in our example here, this is an A cycle. Okay, so it's the cycle around that vertex. And this is a B cycle. And that is a C cycle. Okay. And now I can tell you what the relations are. Very beautiful. I mean, if you want, you can just see this as a nice procedure to produce very interesting finite dimensional algorithms. So the first thing is, so the relations now, these are relations for the relations for arrows in the quiver. Okay, so now I'm talking about arrows in the quiver, not edges of the graph. The first thing is that alpha of beta is 0 if alpha and beta are not part of any cycle, not part of any V cycle. So over here, for example, going dunk, dunk, that's not part of a V cycle, so that composition will be 0. Whereas dunk, dunk is part of a V cycle, that composition is not necessarily 0. Dunk, dunk is 0, not part of a V cycle. Yep. 2. For any V cycle, alpha 1, alpha 2, alpha m. So this is doing 1, 2, m. Depends how I decide to order my composition in the quiver, but I'm not going to worry about that. We have that. So this is called C. Okay. C to the J, the alpha 1 is 0. Okay. So what that says, sorry, C to the M, where this is the multiplicity of V, and it's 1 if V is not an exception. Okay, so for example, here I have a non-exceptional vertex, so my relation is dunk, dunk, dunk is 0. So going around a cycle and 1 more is 0. Whereas here, my relation is this loop to the m plus 1 is 0. And lastly, So if we have C and C prime are V respectively V prime cycles starting let's say the edge. Graph, we can show vertex. Quiver. You have C equals C prime. Okay, so here, for example, here are two different. Here's a B cycle. This is an A cycle. This is a B cycle. This and this both start at this point. So here my relation is that this is equal to this. And then that's it. And the claim is that this algebra describes B when B has cyclic defect group, and I haven't told you exactly how to go from B to the quiver, but I almost have. I've told you what the graph is, I haven't told you what the plane root is. Yeah, so we read the graph off the decomposition matrix. Don't worry if you don't remember, I'll give some examples now.
Wait, is it clear that this algebra determines the quiver? I mean, sorry, that it determines the tree, or that it determines the quiver? Again.
Good question. What do you reckon?
Doesn't seem immediately clear. Or even if things are finite. So what was the question? So from this description, how would you recover the graph? Like without knowing the chosen generator.
You have the
You have the algebra.
oh,
So firstly, let's answer Chris's first question. Is this a finite dimensional algebra? Daniel says yes.
Can you just remind the definition? So the basis is the all part, set of all parts,
All paths.
modulo these relations.
Yeah. And multiplication is concatenation of paths. So Daniel puts in a vote for finite dimensional, as does Geordie. Anyone else want to vote finite dimensional? As does Joseph. I don't know if Nick is. He's ambiguous. Yeah. So might be. So what's an argument, Tasman? What do you reckon?
Well, if the path goes outside a cycle, it's zero because two arrows that they're in different cycles are immediately zero, and if the path that stays inside a cycle, well, it must eventually end by the second relation.
Bang on, yeah. And then, you know, we even didn't need the last relation in order to do this. Great. What was now that was the easy question. Now the next question was how do we recover the quiver? How do you recover, Mr. Sherman? I give you a finite dimensional algebra. How do you go about recovering a quiver?
Oh, sorry, no, you go.
That's you're Mr. Felt.
Right.
That's Mr. Sherman.
okay. Maybe we the same last name. I didn't.
So what do you reckon, Alex?
Oh, I think to recover, well, first you get the graph, but I think the symbols.
You get the vertices, yeah.
Sorry, the vertices, and then the number of edges between them is determined by X groups.
Mm-hmm.
And then the relation is determined by computing composition of morphisms between projective objects as far as I understand.
Yes, Joe.
Question about the third relation.
Sure.
It seems like in the A and B cycles that you've drawn up there, I can do a B cycle and do it. Oh, no, ignore it, because you can only do it once.
Yeah, sorry, I was gonna say it looked like you could kill going around twice by just doing an extra edge and then popping it when I something, but it's already dead.
So I would really encourage you, if you want to think about this stuff, I mean, it's very fun to think about, I think. If you want to think about recovering the quiver from this algebra, think about the structure of the indecomposable projective modules. And it turns out they have a beautiful combinatorial description that can be read off the graph. And I'm not going to tell you how. I'll give you a little hint in a second. So let's do some examples. This is the source of the second errata. So if we took B star, 0 star, star, inside SL2FP, and then we look at the principal block of KB, where the characteristic of K is P, then the Brouwer tree was following, well, so I'm telling you it's following. And so edges in the Brouwer tree correspond to characteristic P symbols. So edges correspond in the graph, correspond to vertices in the quiver, correspond to isomorphism of symbols. So these correspond to mod P symbols. And so the vertices in the tree correspond to characteristic 0 symbols, but it's a little bit subtle, except for the exceptional vertex where you generally have multiple characters. So and you'll see that the relation, yeah, so I should say the exceptional vertex is the induction from U to B in the notation that we were using last time, chi0 plus chi1. But feel free to ignore that. I just when we had when we saw the decomposition matrix of B, it looked like 1 1 1 1 1 1 1, and then 1 1 1 1 1 1 1 1 1, like that. And this is the exceptional vertex. There's this. And the relation maybe I'm allowed to mean one more time and write down the quiver, and then you should tell me what the relation is.
So Geordie, is that matrix for the like projectives and symbols in characteristic P, or going from 0 to P reduction?
So this is my notation for the decomposition matrix, which I hope is standard, where I have my characteristic 0 symbols. And here said these rows are what happens when I reduce mod P, and these are the characteristic P symbols. And so Brouwer reciprocity tells you that the columns are what happens when you take an indecomposable projective, lift it to characteristic 0, and then decompose it. So what this is saying is that there's this funny thing that occurs in the lift of every single lift of a projective. Yeah, I said something twice there, but anyway. Okay, so what's the relation? There's pop quiz.
Go around twice plus 1.
Exactly. Yeah. So go around twice plus 1. Zero. And somehow, for some reason, I convinced myself it was twice plus 2, and that was my mistake on the board. So that's the mistake last time. I think it was two lectures ago. Okay. So now, I just want to, at some point we should be So the plan, maybe I'll just say a little bit where I plan to go in the next couple of lectures. So this is the last lecture on this kind of what I would kind of call modular representation theory of all finite groups, where we try to do it and we discover it's very hard. And you know, we spent like a lot of time just on SL2 and B. You know, it's not easy. And then I want to go now from the next lecture into symmetric group land. Okay. And then there's just an incredibly rich and vast theory. And you have so much more techniques because everything's very, you know, there's a zillion beautiful things that can be done. Okay. And so I'm hoping that over the next kind of weeks, we get some kind of reasonably intimate knowledge of decomposition matrices for symmetric groups in small examples. And this is, I'm just kind of doing a warm up here. So some of this will be explained. Maybe you saw this already. S4 equals 3. We get the following decomposition matrix. There's a strong chance that I'm going to switch to French notation for partitions once we start doing the symmetric group, but I haven't done it yet. 1, 1, 1, 1. And so I'm not telling you how, so this should be familiar. These are the characteristic zero representations of S4 in the principal block 4 equals 4, 3 equals 3. And then these are the representatives of simple modules in characteristic B. And somehow you can work out from this decomposition matrix how I'm parameterizing them, or I can explain in more detail later. And the Brouwer tree is, so I can label non-exceptional vertices by irreducible characters in characteristic 0. This is the Brouwer tree. And there's no exceptional vertices. So what is, here's a question for you. What is the C log P subgroup, or what is a C log P subgroup of a symmetric group?
Like of that symmetric group? I'm confused by the question.
Well, yeah, what is it in this particular example? I heard someone whisper it, tree cycle, yeah? So when would, let's just apply pure thought to this. Put your hand up if you've thought about C log subgroups and symmetric groups before. Okay, great. So it's a little, we can have a little bit of a fun bullet exercise. Yeah. So how do we start thinking about this? Like, what would be your first thought?
About just a general symmetric group, we're taking some pseudo subgroup for some P?
Yeah.
Okay.
Let's just do an example. Let's do S6. Yeah, so
Equals 5.
yeah, so like if 4 is reasonably small with respect to the prime, it's easy, yeah? Because it's just a P sub. So we just get a Z1 P set as our single P subgroup. Now, where does this argument start to break? Like imagine that I'm saying, okay, can I do S5? Yeah. S6?
Now you can get another, which you can get another P cycle. And then
Yeah, so now so you've got 6 factorial. You know, it has a 6 in it, and it's got some other stuff, and it's got a 3 in it, and it's got some other stuff. Yeah. So there's 2 3s there. So it's 3 squared times something. And how do you find that on
State disjoint. Sorry, 3 cycles.
Right. So we did S6. Where do you think the next problem is going to be?
It's 9.
S9, yeah. How often does 3 divide the order of S9?
4 times.
4 times, yeah. So it's 3. There's in the 3, a 6, and in the 9 twice. Yeah. So now, what are we going to do?
And the thing that permeates the partition, the 3 things.
Exactly. Yeah. So you get 3 cycle, 3 cycle, 3 cycle, and then there's a big thing that commutes them all. Yeah. And if you fancy, that's called a Reef product, I think.
Yes.
Yeah. And then you can start seeing what C-log subgroups look like in symmetric groups in general. They start looking like more and more complicated Reef products. Wasn't that a fun little exercise?
Is that saying that the Brouwer trees for symmetric groups are always lines? Because the only cyclic subgroups are the trivial ones? Or?
No, you can have a Brouwer tree can be very interesting. Like a Brouwer tree, just because your defect group is Z1Ps, it doesn't mean the Brouwer trees are aligned.
Well,
Oh, yeah,
Yeah, like, we
Yeah.
saw over here.
fair enough.
That would be
Yeah.
interesting. I think, yeah. So the brow trees of somehow brow trees of symmetric groups, it's very rare for to be controlled by a brow tree. And I'm only seeing lines, but I'm not sure if that's a general phenomenon.
Right.
You said that the brow tree determines up to Morita equivalence?
Yes.
Oh, wait, but it also sounded like you said the brow tree determines the algebra of the block. What does it only determine Morita equivalence task algebra?
Well, what's the difference between Morita equivalence and an algebra?
Isn't like you can have Morita equivalent algebras which are not equivalent to algebras?
Yes, which are not isomorphic algebras, yeah.
Yeah.
And the basic thing that goes wrong is you can't dimension of a simple is not something that's well defined under equivalence of categories.
Mhm.
If I have a 7-dimensional irrep and I look at the subcategory generated by that just looks like vector spaces. You can't tell it's 7-dimensional in the categorical sense. And that's the only thing that changes under Morita equivalence. Is you can like take something that was 4-dimensional and make it 7-dimensional, whatever.
And that does occur.
Yeah, absolutely.
Oh, right, yeah, the trigger. Yeah.
I mean, it occurs all the time.
Mhm.
So more generally, if we do this, so this is just a line, no exceptional vertex. Then our brow tree. Okay, so I have one vertex for every edge here. And if I call these E and these F, by abuse of notation, my relations are E squared equals F squared equals 0 and EF equals F. Okay, so E squared, that's the fact that these two E's are not, so the abuse of notation is I'm not kind of saying like I should really call this E1, E2, etc. But there's only one way to assign labels to this so that makes sense. And these become the relations. And yeah, so this going twice is 0 is the fact that these are not part of the same V cycle. And then the third relation tells me they're going around like this. The same thing is going around like this. And I just thought it'd be nice to do, so if we do the following example. I just wanted to show you the indecomposable projectives. So this would be S0, S1, and S2. So these are the, I can't remember what these diagrams are called, Lerby diagrams? Something diagrams.
Maybe filtration, yeah.
So what I have a projective, and what I write down is the associated gradient of the radical filtration on the projective. So the first one goes S1, S0, S1. Next one goes S1, S0 plus S2, S1. So this would be P, the projective cover of S0, like this, and projective cover of S2, like S2, S1. Okay, so this is the socle. This is the head. And these indecomposable projectives were over a symmetric algebra. So that means if I turn any of these indecomposable projectives on their head, they should be the same thing. So they're self-dual, and we can see this manifestly. And you can also see very beautifully.
What did you just say? Sorry, Geordie.
You have to give me more information.
Oh, you said because something through, it's the dual if you.
I agree.
Yeah.
What's true statement? No. We're over, so KG is a symmetric algebra. Which means that, so what that means is that, well, what it implies is that KG is isomorphic to its dual. So the regular representation is self-dual. And what that tells you is that injectives and projectives, indecomposable injectives and projectives coincide. And so if I take the dual of this thing, this is the indecomposable injective, but it's self-dual, so it's isomorphic to itself. Yeah? And you can see this, if I turn it on its head, I get the same thing. If I turn it on its head, I get the same thing. If I turn it upside down, I get the same thing. This is what you see in the setting of a symmetric algebra. And you can see the relations in this quiver. If you're used to it, you can just stare at these projectives and see the relations in the quiver. So, like so the first thing to remember is that, so this is my quiver. But the first thing to remember is that these maps in the quiver can be interpreted as maps between indecomposable projectives. So really, I secretly think that this is sitting here, this is sitting here, and this is sitting here. And now there's a map from here to here, which kills the circle and maps that S0, S1 to here. So it's really fun. And is this like semi-obvious to people, or should I go do it in detail? Because it's really nice. May as well do it in detail, yeah? It doesn't look like it's semi-obvious to people.
Yeah, I'd appreciate it in detail.
Also, Geordie, are these Lerby diagrams, are they what have previously been called egg diagrams?
Yes, I call them egg diagrams in my head.
Yeah, okay, cool.
What diagram? What thing?
I mean, I just call them egg diagrams because they look like eggs usually.
Is this related to the symmetric group, or this is just a random graph? Just
if I went one more symmetric group up, it would be a block of the symmetric group. Yeah. It's also, the reason I'm doing this example is because this example is a little bit like, it's like the first interesting non-semi-simple category that you see in representation theory. It shows up in many different situations.
Is there another name for this algebra?
Pre-projective algebra of type A equivalent. Yeah. And it's really beautiful that it kind of, it shows up in geometry, it shows up in algebra.
It's possibly the Modular of pre-projective algebra, but anyway.
You're probably right.
It doesn't matter. So.
Yeah, you're probably right. So, I want to redraw my diagrams. So this is how we would also argue that we can recover the quiver if we wanted to. Okay, so it's really important that these things are uniserial. So this means this is the unique simple submodule. This is the unique submodule of, with two simples in it. Like this has a unique composition series. So what that says is that if I'm going to map this anywhere, to it something indecomposable, either it is an isomorphism or I kill some part of it. And if I kill some part of it, the smallest thing I can possibly kill is to kill this S0. And then if I do that, I can map this bit over to here.
And that's the only way you can map it in. Like this one-dimensional.
Yeah, that's all. That's the basis for the space of maps. So this map F E spans from P0 to P1. And now, if you think about going back, there's also only one way. I have to kill this S1. This S2 doesn't occur here at all, has to die. So this bit here has to map into this bit here. So I have another. I have another map here, kills these two things, and maps this bit down to this bit. And this F